how can we learn everything that we have learned about data and statistics so far in stock markets? This is exciting, right? What if you could pick a stock portfolio that is so good that it doesn't vary that much, that it gives you a positive return? Can we use the skills that we've learned so far in statistics and data analysis to the stock market? Yes, we can. So let's get into it. There are two concepts, alpha and beta, when it comes to stock market. And these are different, alpha and beta, that we have seen so far. For beta 0 and beta 1 is different than this one. Alpha is basically when we say, hey, what is the alpha of a stock? Alpha of a stock is what is the return of a stock when you have zero returns on the stock market overall. So let's say when the stock market doesn't give you any return, zero returns, what is your current stock's return? If it is positive, then you have a positive alpha. And we can use the regression that we have done so far, where we have a prediction line. So let's look at the prediction line. How would we build a regression? We would say on the explanatory variable, we would take what is the stock market's overall performance, and on the response variable, we could say, hey, I want to understand, let's say for Microsoft, what is the Microsoft stock performance percentage change compared to, let's say, S&P 500 or any stock index. So you can compare your stock's performance with the market. Think about this as the baseline. If you could just buy the market overall, but if you don't want to buy the market overall, you want to say, hey, I think this company is better. Let's take this example of Microsoft, right? So if you want to compare Microsoft with the stock market, in this case, let's say VTSAX, which is the total stock market index fund. And so your alpha, if it's positive, that means Microsoft is a better investment. On an average, it gives you a better investment than VTSX. So let's look at this x-axis, and this is 0, 0, meaning when the stock market gives you zero returns, if your alpha is positive, meaning if you have 0, something positive, let's say 2. So in this case, it's saying when the stock market gives you zero returns, Microsoft will give you 2% alpha. Great. Isn't that great? Like when the stock market does nothing, you get positive. And when the stock market, let's say, is giving you a positive return, like 1, 0, then your alpha could be like, hey, 0, 1, 3, right? So now you're getting an above average return than what you would have gotten just from investing into the stock market. So plotting the baseline with the response variable, your explanatory variable with the response variable, this is all that we've learned in data analysis so far. Trying to regress what is our explanatory variable's response to how does my response variable change, right? So if we can plot this regression line, like by getting data about percentage stock returns over the last 50 months for stock market and 50 months for Microsoft, and then we do a regression plot, we will get the intercept, the coefficient. This coefficient in the regression is your alpha. When we run a regression analysis, we get a coefficient. That coefficient is your alpha. If it's positive, that means you have a really good stock that you have taken. So that's alpha. What is beta? Beta of a stock is the slope. So that is beta, right? When let's say stock market went from 0 to 1, what did your company or your current chosen company do? Did it have a positive variation or a positive variation? Yeah, is it or a negative variation? Meaning, is it when the stock market is going up, is it going up or down more, or is it going up or down less, right? So it's basically beta is like how much change is your stock. It's volatility. Beta is volatility. Yeah, beta is volatility. So how much volatile is your stock with this baseline? So let's say this is your baseline, And if your beta is if your stock is like so volatile, right, then your beta is high. It is, on an average you will see positive return, but you will see lots of volatility. So alpha is the additional edge, beta is the volatility. Like if the stock market goes up by 1%, your stock can go up by like 5%. So that's your slope, right? The slope of how your company varies with the baseline changes. So you ideally want stocks that don't have lots of variability, because you could invest at the peak instead of at the bottom, right? So you might get in here, and then it can go down quickly, and so if you watch your stock market performance, then it affects you. So this is powerful. If we want to create a portfolio that has low beta and high alpha, then we will have a portfolio that is good. It's just keeps going up and up and up, right? So that is an important learning. How do we use linear regression to now pick a portfolio? Now let's say, how do we use this idea not just to pick a portfolio that has high alpha, low beta, but also, like, let's say you have one stock. Now you add the second stock. We have learned MRM, SRM for one variable. We could do MRM, right? So we can not just look at one index. We can also look at, like, hey, some other index, which could be a different variable, a small cap index or something else like Russell's. So we can use MRM as well to add more variables to our returns, right? So now, what we did for one company, we can extend this to build a portfolio. What if instead of one company, you now plot the percentage return of, let's say you want to buy Facebook, and now you plot a combined percentage return. Now all of a sudden you can say, hey, is my portfolio's alpha overall? So you just take Microsoft's percentage return change, Facebook's percentage return change for that month, for the last 50 months, add them up, and then you'll get the combined variance. You get the combined variance, and now you have one number. That is your portfolio number. So now you can check your portfolio versus the stock market overall. If you add a stock that increases your alpha much more and decreases, increases your alpha, which is your edge, and decreases your beta, then that's a good addition to your portfolio. It's going to be much more stable. It's going to be much more healthier, predictable return. So that is important too. Not only does it give you an edge to select a high alpha stock, but it also gives you a mechanism to build a portfolio now. So capital asset pricing model is one such model that has lots of insights. But the two key ones are risk versus return, right? This is a risk. If you have high beta stocks in your portfolio, it's a risk because you could get in at the very high peak of that curve, of that cycle, because they all have cycles. But there's also a risk versus return in the sense that if you want to buy high beta stocks, like in this case, let's say Amazon, right? So now let's transition into this graph. This is a very powerful graph. It plots alpha versus beta, right? For a given company, it says, and it does for so many companies. It's from 2019, end of 2019 data for many months. Alpha versus beta. Look at this. Facebook, very high alpha, but very low beta. Amazon, super high alpha, but super high beta too. IBM, right? Like it's lower alpha. It's actually negative. And then Amgen, Google, right? Somewhere in the middle, right? So now all of a sudden you can compare these companies, and you ideally want companies in this segment, right? Because then you have low variation. This is the amount of variation. The way you would want to read it is that here there is low variation, meaning it will not change too much, but here it will keep increasing the variation, right? So the more you go on this axis, there's more variation, up and down movement, daily change. You will see volatility. Tesla maybe will be like super high up here, or maybe here, I don't know. But so look at that. So variability versus like gain, and you want to go as much to the top so that you have a lot of edge. Your stock is better than the index. But high level insight is, it's very hard to beat the market. Warren Buffett Google this. Warren Buffett has done a lot of research and bets that he's won, that it's very hard for you to build a portfolio that beats the market overall on a longer period of time. So even this data, right? Like this data is 2019, but this data for Facebook might have changed completely in 2020. So you would have to look at the data, and you'd want to keep looking at the data, because the data changes. Companies change. What happened in the past may not happen in the future, right? So this capital asset pricing model gives us a good insight into building a portfolio that we can understand has high alpha. We also want to reduce beta, and we also can build a mixture of portfolio which is diversified and it balances each other. So this is a pretty interesting thing to do, to find out like what companies do you own, what are their alphas, what are their betas. I'm going to do that analysis as well. That was the biggest learning for me from this. It's like, hey, how are my companies alphas and betas? I can actually do this in Excel. I'm going to do that. All right, so how do we not only use this to apply this in our real life, right? Stock markets, building a portfolio, all of the things that we've learned. Now, what if I told you, can we use what we have learned so far to build a self-driving car? Can we use everything that we've learned so far? We've now done, hopefully we'll make a lot of money, right? Because we will be building the best of the portfolios, right? But can we use this to predict and build systems that are not built yet, right? In a self-driving car, what's happening is it's trying to predict whether to stop or whether to hit the accelerator, whether there's a problem, right? It has to do a lot of those analysis and decision. So when you have those complex problems, that's where machine learning comes in, and we can use all of this data, all of this analysis, and all of the skills that we've learned in data and statistics so far, and that's the basis of machine learning. Machine learning, in a sense, is basically, what we have done so far. We have calculated a regression line that looks like this: y hat equals beta 0 plus beta 1 x1 x2 x3, right? This is an MRM. There's a coefficient intersection, and there's a slope. So machine learning helps us build this, and it helps us build this without us having to look through the data. Right now, what I did, I had to say, hey, I want to look at percentage return on the baseline. I have to say, hey, this is my company. What if you could use a software that told you, hey, what should be your stock portfolio selection? What should you do, right? What if it told you that? And that's what machine learning does. Machine learning takes lots of data. It can understand lots of variables. In this case, I just took one variable, right? Stock market. What if I could say, hey, my percentage return doesn't really just depend on the stock market. It depends on the oil market. It depends on the currency market. It depends on what's the temperature, or pandemic situation, or so many things. When you have a problem like self-driving car, there's lots of variations, right? There could be raining. It could be raining when the car is being driven. It could be very foggy. It could be nighttime. It could be daytime. There could be a stop sign that's not working. So when you have lots of variations like this, that's where machine learning comes in, because it's very hard for you as a human to come in and say what factors are important, what factors should I add into this decision-making process. That's where you want the machine to figure out with algorithms. So machine learning has two things. You do machine learning when you have complex problems that even you can't fathom. You can't fathom as a human what are all the variables. It's very hard, like self-driving cars, detecting some sort of diseases through pattern recognition, through image x-rays, and a host of other things that humans have gotten better with. But machine learning can do that when you have lots of data, number one. If you have lots of data that is very complex, lots of explanatory variables. If you have lots of explanatory variables, and if you have lots and lots of data, that it's very hard for you to go through all of that, then you need machine learning. So machine learning, two key requirements. It's the exact same thing that we've done. It's the exact same model that's being built. This is the model that's the output of machine learning. And so you do that only when you have lots of variables. It's a very complex use case. And you do that when you have lots of data. And we do the exact same thing, but it becomes much more complex. So complex that there are courses for this. There's that I'm excited about now, because now I understand like all of the things that we've learned in statistics. This is now a foundation that we can build on and explore machine learning in a much better way. But in a sense, machine learning is an algorithm that finds for you beta 0 and beta 1. And in this case, if it's MRM, beta 2, beta 3, beta 4, and machine learning can go to millions of such variables and weights. So that's the power, right? Like you might think that, hey, driving is easy and I can tell you like those 10, 15 things. It's not that easy. We have learned our brain is a very complex instrument, and it has figured out millions and millions of weights in our neurons, and we think it's easy, but it's not really easy when you tell the machine to do it. And so that's where you need machine learning. So it figures out with lots of data, and it watches what would the human do. When it watches what the human does, it learns from it. And then it says, hey, what were the variables that I should have given weight that would have predicted me to do this? So machine learning helps you with prediction, right? There are lots of predictions that we can do it. So there are 5 steps in machine learning. Data collection, which is very critical and important, because whatever data goes in, that's going to be, machine's not going to ask you whether that's the right data or the wrong data. It's just going to take it at face value. So data cleaning, data collection, data standardization is a very, very big subject where we have to give machine the right data. Then you have to build a model. Like we've built so many models, right? SRM, MRM. So it will build a model. This is where human judgment, lots of training in machine learning is important, because what model would you use? Would you use an SRM, MRM? Would you use a convolution neural network? Would you use decision trees? Would you use random forest? And there's so many, jargon terms, and there's so many types of algorithms. What algorithm would you use? That is where a lot of training is needed to understand like what model would you build. And then you have to do training, which is basically once you have selected the model, you want to train it to adjust the weights, you get the right weights. And then you do cross-validation, so that you take out all the spurious variables. That's a little bit more tuning. And then you do test, where you say, hey, is this algorithm working or not working? If it doesn't work, throw it out, start again. And then you deploy it. These are the steps. And then there are a lot of other concepts that are important. When you fit the data, when the machine fits the data, if it fits the exact 100%, then one new data point, it will just blip, right? So overfitting is an important concept. Underfitting is equally important. You don't want to be too bad at prediction. Collinearity, this is critical. We've learned about collinearity, where if I were to add a variable here that's entire stock market, and if I add S&P 500, if I add another variable that is like Russell 5,000, and then if I add NASDAQ, then they all have a lot of overlap. They all have a lot of correlation between them. And so collinearity is an important concept, because machine learning also helps you with taking out some of those collinear variables out of your equation. So collinearity is important, and bias, right? All of these terms that I'm using, it's like a subject in itself, which requires inquiry, it requires deep mastery and knowledge, but it's this statistics and data sets us up to learn those concepts, right? And then there are these algorithms that I talked to you about briefly: lasso, decision trees, neural networks, CNETs, convolution neural networks. But in a sense, neural networks is nothing but it breaks down those bigger problems into small problems and then connects each of those problems. They can think about one output connected to the second. If this is your output, then it is connected to the second one, the third one, the fourth one, the millionth one, right? Decision trees it's cutting the data. It's like figuring out like, how do I cut this data? And then building the tree. And then it just goes through the tree, builds the tree, and then cuts the data. And then there are lots of cloud infrastructure that can be used. Microsoft has Azure, Google, Amazon Web Services. There are lots of machine learning tools and algorithms that you can use. But remember, you only go there if you have lots of complex use cases that you're trying to solve for. And you have lots of data, because machine learning only works once you have lots of data. If you don't have lots of data, if you don't have the infrastructure, if you don't have a complex problem you're trying to solve, don't just go to machine learning. Use Excel. Most of the time we can solve it with Excel. We talked about collinearity, but like detect collinearity, if we add all of those 4 variables, we will see that the standard error goes up if we add the more variables, we'll also see that F statistic goes down, right? Adjusted R square goes down. Those are signs of collinearity. And so what you do with that is you one by one remove variables and then check whether your adjusted R square is going up, F statistics is going up, and your standard error is going down, right? Then you can easily check for collinearity. And very simple is to just check for correlation. You can build this again, build a correlation matrix in Excel, and you can see, hey, there's high correlation between these variables. So powerful, powerful, powerful. We learned how to build a portfolio. We learned how to build these models for complex use case, and this is a subject in itself, machine learning. When you have complex data, you build a model, you collect data, you train it, you cross-validate, you test and deploy. There's like a subject. Each of these are subjects in themselves. Each of this is a course in itself. So it's like huge set of things, but this is the basis. If you don't understand how to analyze and analyze your data, if you don't know the basics of statistics, then none of this works, because it's all built on that. Algorithms as well. All of these are nothing but algorithms that will, minimize sum of least squares, right? That's the basic. Lasso, it's nothing but least, absolute, shrinkage, and selector operator. A lot of words, but it is, in a sense, it's basically minimizing least squares. It has a threshold alpha, which says, hey, I only want the variables that have the maximum impact, and so on and so forth. You can use those algorithms that are built. Instead of writing, hey, if there's a red light, then do this. What if there's no red light, but you still see someone? You'd want to stop, right? So that is what the machine figures out with data, by reading and learning through lots and lots of data. So very powerful. We learned how to build a portfolio. We learned a little bit about capital asset pricing model. I am super excited about looking at my portfolio and looking at all the alphas and betas of each of my companies, and alpha and beta for my portfolio combined. And I'm going to try and remove one at a time and see if my alpha goes up, beta goes down. I want to hear from you. What does your stock portfolio look like? Are you going to use this? And how excited you are about machine learning after reading all of this. So thank you. This was awesome. I learned a lot. Hopefully this is exciting for you too. And I will see you in the next one. Thank you.